So the good news here is that from here on out, all of our chapters will correspond to the right chapters of the book because the lecture notes, which are referring to the sixth edition chapters, they still line up now with the seventh edition chapters, and we'll never have to worry about that weird crossover we had before chapter 6. So that'll be fun. Chapter 8 is on solids, liquids, and gases. And I'm sorry to say that my lecture notes and class activity sheets are a little bit backwards. And that is to say, the lecture notes for the first 3 lectures, that is on gases, correspond to the second in class activity sheet. And the last 2 lectures, actually, the 4th lecture corresponds to the first in class activity sheet. And then 1, 2, 3, and 5 correspond to the second in class activity sheet, and they don't even go necessarily in order. So just a heads up, I'm just gonna put this out here right now. Your 8.2 in class activity sheet, the first page, this is from lecture 8.5 down to about here. And then this is from lecture 8.1 and then 8.2 and then 8.3, just so you know what to do when you're doing them. And then our 8.1 in class activity sheet, this is a review from chapter 5, because this is directly applicable to the stuff we're learning in chapter 8. And then this is from lecture 8.4. Okay, so my in-class activity sheets do not correspond to the order that it's being taught in the lecture notes, so hopefully don't be completely confused by that. You can just, if you've made a note of these, then that'll help. That'll help. But of course, as we go through it in the lecture here, I'll direct you to the right places. Okay, so here now we're going to introduce gases and the properties of gases. And gases are actually super interesting because it turns out that all gases behave exactly the same or very similarly. And that's kind of astonishing given the huge range of molecules that there are in the world. The fact that if they're gases, they're still going to all behave the same way in terms of physical properties. So those physical properties defined a little bit by what we call the kinetic molecular theory. And here are the tenets of the kinetic molecular theory, and you do need to know these for the exam. Guaranteed there's going to be a question about the kinetic molecular theory on the exam. And this is what we learn about gases. First of all, we're going to say that gases consist of many particles moving at random. And second of all, we're going to say the amount of space occupied by the gas particles is much, much smaller than the amount of space between the particles. In other words, there's a lot of empty space in a sample of gas. Because those gas particles are so far apart from one another, they don't see one another, and so they're not going to have any forces between them because they're just too far. Number 4, average kinetic energy of a gas is proportional to the temperature. I think we've talked a little bit maybe about how heat, which temperature measures heat, that's just molecular movement. And that is a reflection of kinetic energy. So it makes sense that the higher the temperature, the higher the energy you've got. And then collisions of gas particles are elastic, and this is just saying that energy is transferred, it's not created or destroyed. So you could have a gas particle collide with another gas particle, and they might transfer energy between them, might give the other guy a little boost or whatever, but the energy is not created or destroyed, it's just transferred. So it's just a kind of a little reminder, if we were to look at our microscope at particles of a solid, they are stuck in one place and they can't move. Relative low energy state, if we look at a liquid, they're really close together, but they can slide past one another, so you've got movement from place to place. And if you look at particles of gases, you would have particles of gases zooming very far apart from one another, moving very quickly. Everybody with me so far? Okay. All right. So we know that gases have a lot of movement energy available. The fact that gas particles occupy a much smaller amount of space than the amount of space between the particles, that's just to say, if we look at this, we see we've got two little dots, and then mostly it's just empty space. And the practical application of this is that gases are compressible, because you can make empty space take up less space because you're just getting rid of empty space, which is why we can take several hours worth of oxygen, for instance, maybe even several days worth of oxygen, and compress it into a small oxygen container that you could carry on your back or wheel around with you if you were going to go scuba diving, or if you just needed supplemental oxygen as a healthcare patient, essentially. And so that's why we can put gases into cylinders and compress them. That's also why they are expandable. If you have a very tiny sample of gas and you put it in a room, it would expand to fill the whole room, essentially, or to be distributed equally in the entire room. So if I have a tiny vial of like a stinky potion and I stick it in the back corner of our classroom about an hour before class, you guys might walk in during class and be like, wow, what is that smell? Because that gas smell has permeated the entire room. Let's see. Gas particles do not have appreciable attractive or repulsive forces. This is going to become a little bit more interesting when we talk about liquids and solids, because that's completely unlike liquids and solids. And a lot of the physical properties that liquids and solids get come from these attractive forces between molecules. So since gases don't have those, almost all gases will behave in a uniform manner. And let's see, we talked already about kinetic energy and temperature. Okay, so good. Excellent. So within the kinetic molecular theory, measurements that are most often used with respect to gases to kind of track what's going on here are pressure and volume and temperature. So just to make sure that we're familiar with these, pressure is often represented by capital P, and the units that we'll be familiar with are atmospheres, which is given by ATM, and millimeters of mercury, which is also known as torr. There are actually a lot more ways to measure pressure, but these are the two that we're going to worry about in our class. And what pressure is with respect to gases is pressure is just collisions. It's the force exerted on an area. So for instance, another unit of pressure that we don't use, but that might help you envision this, would be something like pounds per square inch. Like there's this many pounds of force being exerted on an area of a square inch. And for instance, atmospheric pressure, so 1 atmosphere's worth of pressure, which is the pressure that the gas surrounding you is exerting on your body right now, is like 7 pounds for every square inch of your body, which sounds like a lot. And it kind of is a lot, but you and I are obviously evolved to handle that kind of pressure. And so it doesn't really bother us to have 7 pounds per square inch. Whereas if we went to the moon without a spacesuit and we'd have far less pressure, then that would actually be disastrous for us, if that makes sense. So pressure is the force exerted on the area. And how would a gas exert force on an area? You guys tell me. Oh, I'm sorry, Robin, I didn't see that question in context of what I was talking about. Chemical weapons, though, are more dangerous because of the chemical reactions that they can undergo than anything else. Explosives are so dangerous because they make gases as products And those gases expand so quickly that it really causes that big explosive force. So this would be why, for instance, nitroglycerin is dangerous, whereas a chemical weapon like sarin is dangerous because of the chemical reactions it undergoes with biological molecules. Does that answer your question, Robin? Sorry, I didn't mean to just keep talking. I didn't see it in context. Yeah, because gases take up a whole bunch of extra space because there's this empty space. So if you have something that goes from a liquid to a gas or a solid to a gas in a very short period of time, then the force that is exerted as it expands essentially blows things apart. And that's the destructive force behind explosives, essentially. No problem. Okay, so force on an area. So how could a gas exert force on an area? Have you guys ever felt the force of a gas on your skin? You've been close enough to explosion to kind of feel that? I mean, hopefully not so close, but you could feel a little bit of if you were not too close to be hurt, but you might have been close enough to feel that shockwave kind of a thing. That would be interesting. You guys have all actually felt this. If you've ever felt the wind on your face. So here's your face. And again, I'm not a great artist. I'm a chemist, not an artist. So here's you, or me, or whoever. Okay. The wind on your face is essentially all these little gas particles, and we can't see them. But these gas particles are moving incredibly fast. And yeah, there's a lot of empty space, but these are really tiny. So there's many, 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 many of them that will be striking the surface at any given time. And when the wind blows, then they primarily end up moving more one direction. Then it exerts more force on your face. And you can feel that extra force as it comes. You can feel that. Has anybody ever been in like wind that was so strong that it kind of threatened to push you over? Haven't been in wind that strong since I was a kid, but I've, it was a really interesting experience. Nobody? You guys are quiet today. You're just listening. Okay. Let's see here. 1 atmosphere is the pressure that's exerted by the Earth's atmosphere at sea level. And 1 atmosphere is equal to 760 millimeters of mercury, or torr. This is where pressure was initially recorded, basically in a barometer, which is kind of like a thermometer, but for measuring pressure instead of temperature. And you're going to use this as a conversion factor, and I will give it to you on the exam. I think it's on your equation sheet, but there's that. So that's pressure. So pressure, force exerted on an area, and that force comes from collisions of microscopic, minuscule gas particles on a surface. Okay, next, volume. What is volume? Somebody tell me. So I know that you're listening and you remember stuff from chapter 1. Total space occupied. Excellent. 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 So basically the amount of space that you take up. And again, for gases, this is interesting because since we can compress them and we can expand them, then we can watch as the volume changes and see how that affects our pressure and our temperature, etc. So you could obviously use like milliliters or microliters or liters, but for gases, we're usually going to use liters, which is given by capital L. But you guys should still know how to convert between liters and milliliters and the like. Finally, we've got temperature. And this is interesting and useful because temperature, represented by a capital T, is a direct representation of the kinetic energy that the gas molecules have. So we're going to want to measure that. That's going to be important. So this was kinetic energy, and we talked about that when we introduced the kinetic molecular theory. For the purposes of calculations that we're going to need to do, with gases, we have to use the Kelvin temperature scale, K. Now, the Kelvin temperature scale is used because it cannot be negative and it's never zero. This is very important. So if I'm talking about gases and I give you a temperature in Fahrenheit or Celsius, you're going to have to convert it to Kelvin, is the important thing. Kelvin comes from the fact, and I think we've talked about this briefly before, that movement energy is our heat energy that we can measure the temperature with a thermometer. So when we have no movement, then that's the coldest we can get. You can't have negative movement. So there is a floor, and so that floor says 0 Kelvin is it. And so the conversions between here, Kelvin, it's going to be whatever your degrees Celsius is, plus 273.15, because 0 Kelvin is negative 273.15 Celsius. And I'll give you that conversion on the exam too. You guys don't need to worry about memorizing that. So let's see. The first thing then I want you guys to do, if we go over to our 8.2 in class activity sheet, and we look at section 3, sorry, it's kind of buried in here. These are the unit conversions for temperature, volume, and pressure, just to get us familiar with doing these for the math that we're going to need to do for gases. Excuse me. So let's just do a few of these here, and then I'll let you guys do the rest of them before you come to class on Wednesday. So let's see, here's a temperature conversion, here's a pressure conversion, here's a volume conversion. Let's do each of those. So somebody tell me, hopefully at least 2 of you guys could tell me and agree on the answer. 23.5 degrees Celsius, what would that be in Kelvin? All right, Katie's got an answer. Anybody agree or disagree? Excellent, excellent, okay. So you just use the conversion of Kelvin equals Celsius plus 273.15. We plug this 23.5 into the Celsius, and 23.5 plus 273.15 gives me 296.65. I agree with that. Okay, excellent. All right, somebody tell me 2.35 atmospheres converting to millimeters of mercury. Need at least 2 people to get the same answer. $17.86. Anybody else? Brooks agrees. Okay. Anybody else? It seems like you guys got that answer and you were afraid to type it because it seemed too big. Is that what that question mark means? No, that's exactly right. So here you guys used the conversion factor that 1 atmosphere equals 760 millimeters of mercury. And here we could just do dimensional analysis. So 2.35 atmospheres. And then 1 atmosphere is 760 millimeters of mercury. And obviously, when you multiply 760 by 2 1/3, you're going to get a really big number. So I'm totally fine with the answer of 1786 millimeters of mercury. Feel good about that. Okay. And finally, 0.2 liters to milliliters. (200 milliliters). Everybody agree? So again, here you're going to use the conversion that 1,000 milliliters is equal to 1 liter. Or you could say that 1 milliliter equals 1 times 10 to the negative 3rd liters, because that's what milli means. And whichever one you use, you'll get the same answer, 0.200 liters. Let's say 1 milliliter is 1 times 10 to the minus 3rd liters. Liters will cancel. If you plug that into your calculator, you should get 200 milliliters. Excellent. Okay, you guys feel good about that? Excellent. Well, that's the end of the first lecture. That was easy.